Good morning and welcome to Humpkey Study. I think today we'll have a look at more integration. We'll do integration now for quite a while. We've got a little things to cover here. But the first one is fairly straightforward. These are called triple integrals. Treats these as if they're completely different, but they are not. They're exactly the same issue. A single integral 0 to 1 of a function f of x d length, integrating with respect to length, or dx. This is a Riemann integral, and at each point x of the domain, you have a function value, f of x. Then the integral adds up these function values in a continuous way from over the domain, 0 to 1. If this is a double integral, then you're integrating with respect to area. Area is your key. The book puts a second integral here. And now we're integrating over a planar region, in this case a rectangle. Add up these values, will give you a volume. If you integrate with respect to area, it gives you the volume under the curve. Triple integral, almost the same. Except now you've got a z value up here, and you're integrating with respect to three-dimensional measure, volume, which means now pictorially this is going to happen in four-dimensional space, but you can kind of picture this by putting the x, y, and z coordinates here, the next coordinate w here, and you've got some domain here, and I'll make it look like a line segment, but this is not a line segment. This is just a domain. The fact that it's got interior means that it's got interior, so it's a domain, and you integrate with respect to volume means that you take any x, y, z in here, and you add up the lengths over the entire domain. And this gives you this is measured in four-dimensional measure. So this will be the four-dimensional hypervolume of the region under the graph, which is a real four-dimensional region. So the idea of this, or higher dimensions, is exactly the same. Triple integrals in the book, they use 3. As I pointed out, this can't continue. So this is not, modern notation is just to use one integral sign, but to know you're integrating over. Again, the real problem is how complicated the domain is. We'll write this as an iterated integral. And so if you write it as an iterated integral, the problem with integrating the function is a one-dimensional problem. The real problem is setting these up if the domain is complicated. So in this case that I have right here, you could write this as an iterated integral in many different ways. But if we did x first, x would go between 0 and 1. If we did z next, z would go between -1 and 3. And then doing y last, y would go between 1 and 2, and there you go. So now you've written it as an iterated integral. Each piece is a one variable problem because x is your only variable here. Y and z are fixed. So you treat y and z as constants. That's what I mean. It's a one-dimensional issue. All right. So And the book has some examples to show you how you do this, but in a way you already know how to do this process. The problem is what happens if your domain is not rectangular. And I'd like to take a look at a couple of different versions here. Suppose that your domain is tetrahedral. That means that there are 4 points in your domain, and they determine a tetrahedron. And how do you deal with that? So I'll call that T, and T is equal to, the same word is used in analysis as in linear algebra, span, but we don't want to use the span. We want to use the convex hull. And I'll tell you what this means in a minute. And let me give you 3 points. Let's just take 0, 0, 0, 1, 2, 0, and 0, 0, 5. It doesn't really matter. I picked the points fairly easily so that we can see what's going on here. So we want the, quote, convex hull of these points. And I'll tell you what the convex hull is in terms of just a picture of it. So if you have the convex hull of 2 points anywhere, you can think of taking these 2 points and taking a bag and covering those 2 points and then shrinking the bag. If you shrink the bag, use your hair dryer and blow hot air on it, it shrinks down, it contains the 2 points, but because it's a bag, it'll contain everything in between. Or if you take the 3 points, 1, 2, 3, put a big bag about it, and then shrink wrap it, then what you would get is just the triangle for those 3 points. If you take 4 points, like we have, bag about it, shrink wrap it, you get exactly the tetrahedron containing those 3 points. And I'll also show you what this is arithmetically. So looking at a picture here, we'll talk about this integral in a minute, so I'll erase this. So let's actually take a look at these 3 points. We need 4 points here. So let's take one more. These 3 determine a triangle. So let's take 2, let's take 4, 0, 0. So that we actually have a tetrahedron. Okay, so we have 0, 0, 0. 1, 2, 0. 0, 0, 5. So far, those 3 points determine a triangle. And the other one is 4, 0, 0. And so there is our tetrahedron. And we want to integrate over this tetrahedron. What I've drawn here is the convex hull. So let's take a look at the vectors beginning at 0. This vector between these 2 points, I'll call u, let's just call it u. And the vector between the origin and this point, we'll call that v. The vector between the origin and 4, 0, 0, we'll call this w. Now this convex hull is equal to the set of all points of the form S times U plus T times V plus, and I need another one here, ST, let's call it S1, S2, S3. These are my parameters, S3 times W, such that the sum of these is equal to 1. Less than or equal to 1. Bigger than or equal to 0. So the sum of the coefficients is less than or equal to 1. This is the convex hull, and this is how it always works. This will give you this interior. And knowing this description will allow you to parameterize this region in a very nice way. So our first step is parameterize T. And so we'll parameterize T. I'll call it capital T of S1, S2, S3. This will be equal to then S1U plus S2V plus S3W. So this parameterizes this convex hull as with this restriction, S1 plus S2 plus S3 between 1 and 0. So this is the parameterization for T. I want to talk about this in a minute. How do you deal with this as in an integrated integral? But first, let's take a look at what we've got here. So we have the integral over T of f of x, y, and z, d volume. If T is a rectangle, it's easy just to write this as an iterated integral, but it is not. So we parameterize, and then this becomes the integral of f of the x value. Let's see, what is the x value here? This is kind of a vector equation. So this is S1 times U1, U2, U3 plus S2 times V1, V2, V3 plus S3 times W1, W2, W3. And this is what XYZ is. This is what your substitution is. U1, U2, U3, these are given. These we computed or could compute using the vectors that I gave you. So this is equal to S1 times U1 plus S2 times V1 plus S3 times V3. And that is your x. S1 U1 plus S2 V1 plus S3 W1. That is your x. This should be S3 W1. And then the next one is S2 U2, S2 V2, S2 U2, S2 V2, S1 U2. We're looking at the second component here, S1 V U2, S2 V2 plus S3 W2. And that's your Y, and so on. So this expression here will be what you substitute for F. You'll need an expansion contraction factor. So I've just erased the my substitution here, but we sort of remember it. So here you've got an X1, you've got an X, a Y, and a Z, and you've got the new variables S2, S1, S2, S3. So the derivative of the X with respect to S1 is U1. The derivative of X with respect to S2 is V1. And the derivative of X with respect to S3 is W1. So the vectors that we had, U, V, and W, are going to occur in the columns. So this gives you a constant. This is a linear transformation here. So this gives you a constant expansion contraction factor when you take the determinant of this. So the determinant of this whole thing is your expansion contraction factor. Again, we're integrating over a tetrahedron. So this is equal to, I'll just put S1, S2, S3 here. This is what we're going to figure out next. So this is F of this substitution, F of T of S1, S2, S3. The expansion contraction factor is this determinant. And what we have to figure out is what is S1, S2, S3 varying over, where you have S1, S2, S3 all between 0 and 1. So that's what I'd like to focus on now. How does this work? Because this is not rectangular here. This is not exactly rectangular. Okay. So S1, S2, S3, these are our new axes. And the sum of them is going to be less than 1, and they're all bigger than or equal to 0. So everything is going to lie in the 1 by 1 by 1 box. So our whole picture should lie inside this 1 by 1 by 1 box. So everything's inside there. And if you work it out, this condition means that you want the S values to lie inside this particular tetrahedron. And this particular tetrahedron is nice to determine. Right here is this line right here. S1 plus S2 equals 1. And S3 equals 0. And this plane right here in front is the plane S1 plus S2 plus S3 equals 1. And let's see if we can find this little triangle down here. Well, in that little triangle, if we take any point of that little triangle, the S1 value must be between 0 and 1. And once you know that, then the S2 value must be, then the let's see, the S2 value of this was my S1 value. My S1 value is actually right here. So the S1 value must be between 0 and 1. And then the S2 value can be as small as 0, but it can be no larger than this distance here. So S1 plus S2 must be less than or equal to 1. So S2 from this equation must be less than 1 minus S1. If S2 is bigger than this, then the sum is more than 1 already. And once you know that amount, then 0 is less than or equal to S3 from this equation is less than or equal to S1 plus S2. So this is how to describe the domain of this substitution, this parameterization of any tetrahedron. So the parameterization of any tetrahedron depends on the parameterization of this tetrahedron, and this is always the parameterization of that tetrahedron. Now, if I can write the whole thing down. So the integral of the triple integral of f over any tetrahedron is equal to the integral. There'll be a ds1 here, and s1 will go between 0 and 1. I'm writing this as an iterated integral now. S2 will go between 0 and 1 minus S1, and S3 will go between 0 and 1 minus S1 minus S2. 1 minus S1 minus S2. And this will be ds1, ds2, ds3. And then you take your function and you evaluate it at t of S1, S2, S3. I didn't leave room here, but some room needs to be left. And then there's the expansion contraction factor, which in this case is a constant. It's just a number. So every integral of every function of 3 variables over a tetrahedron can be done like this. So far the shapes, the domains that we talked about are first of all rectangles, arbitrary rectangles, arbitrary tetrahedra. So we've got 2 more to deal with, which I'll talk about next time. So the next shape is anything that's cylindrical. And the last shape is anything that is elliptical. And by cylindrical, I just don't mean a round cylinder. I mean, we can have an elliptical base and a height, or we could maybe have a triangular base and then vertical over that. These are all cylindrical in this sense. So next time we'll be able to deal with these two shapes. Other shapes are not as canonical as these. These are special ways you can just handle it. And so we'll talk about those. This should be called ellipsoidal because it's 3 dimensions. So they get more complicated. This is definitely the easiest, is rectangles, tetrahedra. Not too bad. They depend on the parameterization of a single tetrahedra. S1 plus S2 plus S3 equals less than or equal to 1. Cylindrical, not too bad, but these are a little more complicated, but no more complicated than shapes in 2 dimensions. And these are really 3-dimensional shapes. So we'll be looking at the 3-dimensional version of polar coordinates. Well, that's it for today. I will give you some problems involving these two. I'll see you Monday. Monday, we'll also talk about a test. I think probably next week sometime, we ought to be able to talk about a test on these things. I've also kind of rethought the idea of 3 exams. Probably I'll give you 1 more exam and then the final. We can talk about it on Monday. If there are objections, we can give you another exam. In any case, see you Monday, and have a good rest of the weekend.